Hi, my name is Russinovich. I'm Chief Technology Officer of Microsoft Azure. And I'm going to give you a behind-the-scenes look at how Azure has responded and continues to respond to the COVID-19 crisis. This crisis truly is a humanitarian crisis. Tragedy has been unfolding all around us. At the same time, it's forced just about everybody on the planet to adapt to new ways of living. Whether that means now working from home instead of going into an office place, whether it means teaching online and learning online instead of going into a classroom, or staying connected with the friends and families virtually rather than physically. The rise of digital technology usage has been dramatic, and I think it promises changes that are here to stay. It's also had a huge impact on our healthcare systems, and the rise of digital technologies to help us respond and them respond to this has also been instrumental. Huge amounts of data are being collected all the time that we're rushing to analyze to better understand how the virus is spreading, how to mitigate the spread of the virus, how to provide the most effective treatment options, and we're of course on a race for cures. Throughout the crisis, Microsoft and Azure have been focused on prioritizing our most critical customers. And those customers, of course, are the ones that are at the front lines of this crisis as it's been unfolding. It is the first responders. It's the doctors and nurses in the hospitals. It's the emergency management services. It's also the critical government infrastructure that we rely on to keep society operating. And from Microsoft's perspective, we want to make sure that our technologies can help people adapt to this new world of living and learning and working online. So in this presentation, I'm going to start by talking a little bit about some of Azure for Good programs, those programs where we donate resources and expertise to help people that are working to find ways to address the crisis. Then I'll talk about our response framework. As we saw people shift the way that they work and live to online modes, we saw a huge demand for Azure resources and Microsoft Service resources. So I'll talk a little bit about the response framework we applied, which was meeting immediate demand and then optimizing. Then I'll get into some specifics to show you just how that surge impacted our services, including our global WAN and our networking services, and how we responded to increased network capacity, to how we saw huge spikes in usage for Windows Virtual Desktop and Teams, and how we responded to scale up and then optimize the usage of those resources so that we could have Azure resources for use by critical customers in other domains. And how we also applied security services and expertise to help our customers respond to new kinds of threats from actors trying to take advantage of the situation. And then I'm going to conclude by taking a look at confidential computing, a technology that's been innovated in Azure and that we've been working on for several years that could help combine different data sets in service of getting better insights into all those ways that we deal with the virus. So let's start by taking a look at Azure for Good. Azure for Good is founded on 4 guiding principles, just like Microsoft's for Good programs. We don't want to overwhelm the people that we want to help. We want to be outcome driven where we're focused on the most urgent priorities. In the case of COVID-19, it would mean flattening the curve and improving healthcare system capacity. We also want to make sure that we're bringing truly unique Microsoft value to affect outcomes. And then finally, we want to be open and collaborative so we can involve and participate with the whole community. One of the projects we launched is an employee hackathon. We had over 1,000 employees participate, delivering over 180 different projects across a variety of different areas. And some of those projects have actually already made it into production. The one you're looking at here came out of a 10-person team in Taiwan. This one is focused on helping hospitals detect when people are coming into the hospital that might be at risk, those people that have high temperatures and aren't wearing masks. So it consists of AI models that detect face masks as well as high temperatures. It's connected up to Azure so that it connects to apps on PCs and on phones to let healthcare workers know when somebody's entering that might be at risk. It's actually been deployed at the 300-bed Cardinal Tian Hospital in Taipei. And since its deployment, the lines at that hospital to get in are much, much shorter now that this automated system can make sure that people are coming in safely. We've also been developing and delivering AI health bots. These health bots are built on top of a bot service, which is a SaaS app for building AI bots that interact with people in a conversational interface through websites or applications. This frees up doctors, nurses, administrators, other healthcare professionals to provide critical care because patients and potential patients can be interacting with the bot to get answers to their questions. You can see two of the healthcare bots here that we've deployed, a CDC self-checker bot that you can go and use to see if you might be at risk of having the virus, and a COVID-19 Plasma Alliance bot, which can be used to see if you're a candidate for donating plasma to help other people. We've had over 1,300 deployments of the AI bot, including at the UA Ministry of Health and in the state of Washington. And just like the other services that I'll be talking about here, this is built entirely on top of Azure. You can see here the architecture of the AI bot service, which consists of SDKs. At the heart, an AI bot service that makes use of other Azure services like Azure Kubernetes Service and Cosmos DB, and then connects out to apps and websites, like I mentioned, that provide the interface and host it for interacting with the bot service. One of our For Good programs was donating resources and expertise. In this case, to Immunity Bio, a late-stage biotech company that's focused on immunotherapy programs in oncology and infectious diseases. They turned their attention to trying to understand the COVID-19 spike, which is the receptor that opens up and connects to the ACE2 receptor on cells in the respiratory tract to cause an infection. By understanding how the spike works, that could lead to vaccines and better understanding of how the virus might mutate. We donated 1,800 NVIDIA V100 Tensor Core GPUs, which together created 24 petaflops of computing power. This allowed them to simulate 198 microseconds of molecular dynamics modeling of that spike in a single day. Now that sounds like a long time for a short period of modeling time, but what it let them do was process in 2 months what would have taken them 3.5 years on their existing resources. In a similar way, Folding at Home, a project that came out of Stanford for leveraging donated compute resources from home PCs to study proteins, focused its resources on COVID-19. It's arguably the only exaflop computer in the world because of all the donated compute capacity, including compute capacity from Azure. We donated hundreds of GPUs to help them also understand the spike protein. And you can see right here that they were able to model the protein opening up, that spike protein opening up, which you can see it doing in the video there as it attaches. Also made available, if you're interested in donating your compute resources in Azure, a ARM template, Azure Resource Manager template that you can go deploy into Azure and that has installed the Folding at Home client so that your VMs that you donate can participate in further understanding the virus. Another For Good program is in the team space. So Teams is, of course, used in online learning and collaboration, but we also see potential for Teams to be used in events like graduations. Faculty with the A1 faculty license for Office 365 can host graduation ceremonies on top of the Teams platform, including with Minecraft-created campuses. So it's free for up to 20,000 attendees at a live graduation event, up from the 10,000 limit that we've previously had in Teams for a short time to support these graduations that are now going to be remote. Now let's talk a little bit about our response framework. We've published a series of blog posts on the way that we responded. Like I mentioned, this talk is going to go one level deeper to show you behind the scenes in the engineering side of it, how we responded. And when it came to the engineering teams and the response, the first thing that we absolutely had to do was meet the incredible spike in demand that we saw for cloud services of all types, from IaaS to PaaS to SaaS, as lockdowns went into effect. People started to work from home and teach and learn from home. We saw Xbox spike. We saw Teams, of course, spike. And our first goal was therefore to meet that demand by addressing capacity in those regions that were the hardest hit. Now, after we scaled out our services to meet that demand, the next thing we did was start to forecast the kind of demand that we'd see if the spike continued at the rate it was on. We wanted to make sure that we were prepared for that potential case. So we immediately started to implement brownout controls. I'll talk about some of them as we go along. Now, most of these brownout controls we never had to implement, but we had them there just in case the demand exceeded our ability to keep up with capacity. And then finally, we went and started to optimize our services. We wanted to free up capacity as customers continue to adopt our cloud services to make room for them. And so we went into our services like Xbox, Teams, and Windows Virtual Desktop and others that I'll talk about, and optimized their CPU usage as well as their cloud service resource usage. And we also shifted their loads from the hot regions into ones that had available capacity so that our customers would have capacity in those hot regions. The first area we'll take a look at that we applied the framework to is our network. And our network is one of the largest in the world. We've got over 160,000 miles of fiber and subsea cable connecting our 61 regions together. When a network packet enters our network on one region and traverses to another one around the world, it stays completely on that dark fiber network that is managed and owned by us. To connect our network to the outside world, we've got over 170 edge sites where traffic comes in from ISPs and corporate networks into our backbone. And within our data centers themselves, we have over 1 million miles of fiber connecting our servers together. The number of regions we've got is something that is differentiated in the cloud. We continue to add them all the time. Just in the last 2 months or so, we've added 3 new regions, one in Italy, one in Poland, and one in New Zealand. One of the services that saw an incredible spike in usage is our Azure Virtual Private Network Service, Azure VPN. VPN services allow corporate users to connect into their Azure networks, which then can connect to their corporate networks securely over encrypted channels, leveraging Microsoft's backbone to talk between their edge sites themselves, their corporate sites that are in different parts of the world, or from their home PCs. We've got multiple VPN applications, clients that customers can download, and we saw a 700% increase. You can see here on this chart that tracks downloads over time, starting in February and going up into mid-March, of downloads of those VPN clients. And we saw 94% growth in connections to the Azure VPN service during that time. We also saw incredible growth in WAN usage. Traffic connecting our regions together and connecting our regions to the outside world spiked by 40x. And we saw, coincident with that, a 50% increase in DDoS attacks, where malicious actors were trying to take down our corporate customers, which we defended through our Azure DDoS service. Fascinating, you can see a direct correlation between lockdowns around the world and an increase in WAN usage. Here on these graphs, you can see China, which locked down in January 23rd in Wuhan, immediately followed by a surge in WAN traffic that continued to grow out through May. Similarly, in Italy, you can see some WAN usage leading up to the March 9th lockdown date. And immediately after, a 300% and growing increase in WAN usage. And then finally, in the United States, you can see WAN usage that immediately jumped by 60% in some cases after the US lockdown in early March. To meet this demand, we scaled out our WAN. We started by adding 12 new edge sites around the world so that customer traffic could enter our backbone as quickly as possible and not have to traverse between regions. We also increased our peering capacity by 25%, and that meant signing contracts with ISPs and deploying network gear to expand the network capacity into our networks. You can see on this chart, the growth is pretty modest up until the US lockdown and then continues to accelerate after the US lockdown and other countries began to lock down and increased in network traffic grew. In total, we added 110 terabits of increased capacity to our WAN in less than 2 months. Just to give you a concrete example of how we increased our WAN bandwidth, here you can see the 4 network cables that we've got connecting the European and the US continents. One of them, the Maria cable, is one that I've talked about before, one of the largest subsea cables on the planet in terms of the bandwidth that it supports. If you take a look at the network traffic on the Maria cable, you can see that it's pretty constant right up until the US-Europe lockdowns, and then we saw a massive spike. And so we needed to increase capacity on other cables. The AEC cable that you can also see in the picture is the one that we focused on. At the time we ran into this surge in demand, the AEC cable was closed, meaning we didn't even have the physical ability to add extra bandwidth to it. What we required was networking gear on either side that supports dense wave digital multiplexing, or DWDM traffic, which is what traverses over those cables. So what we did, we had another project in another region around the world that was being deployed with new DWDM equipment that we borrowed for expanding the AEC cable, opening it up on both ends. We did that in less than 6 weeks, and we're able to expand the capacity of the AEC cable, which relieved pressure on the Maria cable. The other thing that we did to optimize our WAN traffic in the optimization phase was to load balance traffic. Now, if you take a look at all the ways that traffic flows into and out of the WAN, we've got the internet, we've got our edge sites, and we've got our data centers connecting our regions together. We have a tool called Orcus that we've developed that lets us model network traffic and take into aspects like constraints and forecasts on network bandwidth usage, time of day changes and shifts in network usage, failure modeling. So what happens if a link goes down? What happens to the traffic and how do we reshape it? You can see from the picture that we had many links that were incredibly highly utilized. Using Orcus, we were able to model changes to the network flows across regions, deprioritizing traffic, shifting traffic to different times of days, and with that tool, able to smooth the usage across those links and get everything into a healthy state. So one of the services we relied on to help manage our traffic across our WAN is Azure Traffic Manager, a native Azure service. Azure Traffic Manager lets you create DNS-based profiles to route traffic from outside of Azure to regions that you want it to go to. So for example, your users that are in Ireland can have their request routed to a deployment of your application in our Irish regions. A user that is in the UK would get routed to a UK region. As the spike happened, we saw a 46% month-over-month increase from January to March of ATM usage. What this meant is that we needed to expand capacity across regions for ATM. The team was spending morning and night checking demand, working with our services inside the company to help them shape their traffic across our regions. One of those teams was the team service itself. When you look at this chart, you can see that as users wake up and go to work after a weekend, there are spikes right in the beginning of the morning as they log in. They start Teams calls to talk about what they're going to do in the day. And the spikes, therefore, are offset by several hours across regions because of the time zones they're in. To relieve pressure on our WAN and our hottest regions during those times of the start of the morning, the team service working with the ATM service came up with a plan to shift some subset of traffic for teams from the hot regions to a more lightly loaded region nearby. What they realized as they were coming up with this plan is that they were missing the ATM feature they wanted for this, which is a time-based profile. One where you could say, at 8 o'clock in the morning, shift 20% of the traffic that would normally go to this region to another one. So they came up with an innovative idea, which is to use another Azure service, Azure Runbooks, to create a scheduled task that would go and update the profile at the appropriate times. And with this, they were able to help smooth traffic across our WAN and relieve pressure on those hot regions. Now let's talk about how we optimize some of our services and how we put in kill switches and brownout switches to help relieve capacity. The first one is Microsoft Teams, the service that saw the highest spike in usage, achieving 75 million daily active users, 200 million daily meeting participants, and 4.1 billion daily meeting minutes. You can see very directly on this chart exactly how lockdowns started to shift people into making heavy use of Teams. Now here you can see the Teams architecture. Teams is 100% built on top of native Azure services and tightly integrated with Office 365. So you can see the clients across the top. You can see the core team services in the middle of the picture. It leverages microservices all around it from Office, from Azure Active Directory, and its own microservices that manage chats and video streams. One of the microservices that they focused on was the Chat and Presence microservice. This is the one that's responsible for letting people know when other people are active. For example, typing. It's the one that will show the animation on the 3 dots to show that they're actually typing something. To relieve CPU usage of that service, they decreased the refresh rate. So meaning reduce the polling rate that they would check to see if somebody was actually typing. They also added a kill switch for read receipts, which is the animation that shows that somebody's actually received and read a message that you've typed to them. The kill switch was used in the hardest hit regions at peak load to reduce CPU usage. In fact, both of these kill switches for typing indicators and read receipts enabled a 30% reduction in cores during peak load. The next service that they focused on was Exchange. Now, Exchange is used by teams to go fetch calendar information. And they added a kill switch to stop getting the next week's calendar. And that reduced calls to the Azure Active Directory Graph service by 25%, reducing load on Office 365. They also implemented code optimizations. For example, there's a service that relies on a Redis cache to keep track of chats. And that Redis cache had a deployment per data center. They re-architected that to have one Redis cache for an entire region, and that gave a much higher hit rate for caching, which gave back a substantial number of cores. And lastly, in the logging and metrics area, they switched to a last known good solution for metrics and heartbeats, which saved 2 orders of magnitude of logging volume. And then, like I mentioned, they leveraged the Azure Traffic Manager time-based profiles to shift load between regions and reduce utilization of our WAN. The next service that we optimized was Windows Virtual Desktop, which also saw a giant spike in usage as lockdowns happened, and corporations went from working on PCs in an office environment to working on virtual desktops in the cloud. We saw a 3x growth in just 4 weeks, and Microsoft itself became a heavy user of Windows Virtual Desktop to support our employees. Windows Virtual Desktop is built 100% on top of Azure, just like Teams is. You can see the architecture for it here. To optimize usage and to meet demand, one of the first things we had to do was scale out the cluster partition, which is how traffic enters the Windows Virtual Desktop service and where the RDP traffic flows through. So we added more gateways and front ends per cluster. We added additional clusters per region. We deployed to more regions, and more regions are coming because customers want Windows Virtual Desktop servers to be in the regions that their corporations are in. We also optimized, just like the Teams service did. So one of the services that was being hit the hardest is an Azure SQL database instance that stores information about what Windows Virtual Desktop sessions are active. That service had inefficiencies in the way that it optimized its indices. And so by optimizing the indices, they were able to drastically reduce the CPU usage load on the Azure SQL database and avoid having to scale out. The team also made other optimizations, like leveraging the read-only replicas of that Azure SQL database instance to serve queries instead of going to the primary all the time. That also helped reduce CPU load. And then finally, they increased client-side caches on the front ends of services so that they could avoid going to the SQL database altogether. And finally, they also rebalanced traffic routing to nearby regions to help reduce the load on the WAN. Now, another service that I'll talk about is Xbox. The Xbox Live service is one that people are turning to socially connect, to play online, and also to entertain themselves. We've seen since the lockdown a 50% increase in multiplayer usage and a 30% increase in concurrent usage, meaning the times when people are playing at the same time. We've seen also a 50% increase in daily new accounts. And all of this, when you chart it on time charts, just like you've seen me show previously, correlates very strongly to when countries went into lockdown. For example, here you can see the city of Wuhan lockdown, and usage of Xbox Live apps and games went up to over 180% after that. In Italy, you see the same pattern. Lockdown happens, usage went up to more than 180%. And then finally, in the United States, usage continued to grow after that. Another way of looking at it is the number of daily active users, the number of users that are playing Xbox games every day consistently. And you can see the same thing happen here, where the number of people playing Xbox games every single day has grown to a new level. Now, Xbox is a little bit different than our other services in that we're able to move microservices out of a region to other regions, potentially in different geographies. For example, we shifted our authentication and authorization service back to the US East region from Dublin in order to relieve pressure on the Dublin region. In Asia and the EU, we limited our capacity footprints of the PlayFab multiplayer party chat and game sessions by moving meaningful amounts of the user activity to US East and US West. We also scaled out to meet demand because the Xbox Live service built on Azure is a microservice-based architecture, which allowed us to have targeted scale out of the busiest services. And the result of these kinds of optimizations allowed us to return tens of thousands of cores back to Azure for use by our other customers. In addition, we wanted to make sure that Xbox traffic from Azure to home environments wasn't competing with corporate traffic or teaching and learning traffic. And so what we did is work with ISPs, regulators, and the game publishers to ensure that game updates and releases were only happening off business hours in the particular regions that they were targeting. Now let's take a look at how Azure responded from a security perspective. And of course, there were many new challenges that our corporate users faced as they shifted from an office environment to working from home, as well as IT in helping manage this. With unmanaged user devices, new phishing and ransomware attacks that were taking advantage of the COVID situation, requirement to collaborate remotely but yet do it securely, scaling VPN endpoints and monitoring the traffic across those VPN endpoints, and then also leveraging internal business applications from outside the corporate firewall. During this increase in usage of cloud services, we achieved 300 million active Azure Active Directory users. We saw 30% growth in authentication requests, and we saw 21% growth in third-party SaaS app monthly active user growth, meaning the number of apps, users leveraging third-party SaaS apps, authenticating to it from Azure Active Directory. You can see here the Azure Active Directory architecture, which consists of a number of different core services. One of them that's incredibly relevant during a work from home environment where we need to be even more secure than ever is the multi-factor authentication service. We've seen that multi-factor authentication blocks 99.9% of identity attacks. And it's not surprising, therefore, that we saw a 250% spike in usage of MFA. One of the services that you see in the picture is the Application Proxy service, another service that saw incredible growth in usage as lockdowns happened. What Application Proxy does is allow you to publish web services and line of business apps from inside your corporate firewall so that they're accessible from outside using Azure Active Directory as the way to authenticate them. You can see here on this time-based chart, just like the other ones, early March, the US lockdown, we saw a 100% increase in global traffic and a 40% increase in monthly active users of this service. Other service related to security that saw a massive spike in growth is Microsoft Cloud App Security. That's Microsoft's Cloud Access Security broker service. This one, instead of making your line of business apps available through Azure Active Directory authentication from outside the corporate firewall, actually makes available cloud services to your corporate users through a gateway that controls and monitors their access. It also includes a discovery system that allows you to see what kind of cloud apps your corporate users are using. But where we saw the big spike in growth was in that gateway capability. That gateway capability grew by 100% month over month in proxy load. And you can see the MCAS Proxy architecture before we started to see this giant spike in demand. You can see here it has completely independent deployments across our different data centers. The team had already been on a journey to re-architect it to be more efficient, and instead of duplicating resources, consolidate them here at the gateways so that traffic could go to the appropriate data centers in the appropriate regions, but we could leverage the scaled out front ends across different regions, and that way relieve pressure on the hottest regions. To support that 100% growth, we added 4 new proxy regions. And by consolidating the architecture in the way we did, we were able to reduce resource consumption by 75%. And what that meant is all those freed cores got returned to Azure customers. I mentioned before that we saw an increase in denial of service attacks on our customers. We also saw new campaigns that were COVID related. We saw new techniques being deployed, like Excel VBA stomping, which is a new technique in malicious docs to try to get users to execute code. 30 new crime families in all are what we've seen so far. And in order to protect those customers from these kinds of malicious attachments, whether they're documents or remote access Trojans that attackers would then use to gain control of a target's machine, we leverage a service that we internally called Sonar. It's really a detonation service. So when a user gets an attachment or when they try to execute a piece of code on their machine with Microsoft Defender ATP, that piece of code or attachment gets sent to a Microsoft cloud service, deployed into a virtual machine, which is kind of a lockbox where it actually detonates or runs. And we see what happens. We see if it's talking to malicious websites. We see if it's modifying the system in a malicious way. And that lets us understand, is this malicious or benign? For those malicious ones, we get signatures for them, and then we start to block them and notify our users that they're being attacked. And you can see examples of that, both from URLs and attachments and malicious executables here, being blocked to protect our customers. In a first, we're also making those signatures available to our customers. Any customer that is using Microsoft ATP, Advanced Threat Protection, or Windows Defender Advanced Threat Protection automatically gets protected with these signatures. But in order to help customers that aren't using those services defend themselves against these new kinds of threats, we've published the hashes for them in a GitHub repository here so that they can be incorporated in other security services that you might have deployed. Similarly, we've got a service called Azure Sentinel, which you can think of as a cloud-based SIEM. Sentinel lets you pump data into it from a diversity of sources, including Microsoft's own services, Azure, Office 365. Also, your own on-premises SIEMs and event logging systems can pump data into it. And you get then a common security data pool that you can apply machine learning algorithms and queries that look for specific threats. What we've done is take the queries that are relevant for online collaboration hacks and signs of compromise and publish them so that customers can use them directly on their Sentinel deployments. You can see here a number of different Teams detections, which include new users being added, new applications being added to Teams sites, and we've got equivalent set of detections for customers that are using Zoom. Now that I've told you how we scaled our services, met demand, I'm going to turn my attention to something slightly different, which is an Azure innovation that has huge potential to help us understand and fight the COVID virus. That technology is confidential computing. To understand it, you need to look at the way that we've been protecting data up to this point, where we protect it when it's at rest, when data gets written to disk, gets encrypted. We protect it when it's in transit. When it's being sent between different servers, we use TLS, for example, to keep it encrypted so that nobody can snoop it on the wire. What we've been missing up to this point are technologies that allow you to protect that data while it's in use. If you consider, for example, an analytics job, as it's processing that data that's encrypted at rest, as it reads it in to the server to process it, that data ends up being in the clear. What that means is that somebody with physical access to the server might get access to that data. Malicious insider might get access to that data. The administrator to the server has access to that data. What confidential computing promises is protection against all these threats. It does so by leveraging a technology called Trusted Execution Environments, or TEEs, which are enclaves or black boxes into which you can store the code that will process the data. And that code, once it's in the black box, can't be accessed from anything outside. Not the operating system, not the hypervisor, not the host OS, not even people with physical access to the servers. And that means that your analytics jobs can run inside that TE on the data, and yet that data is effectively encrypted while it's in use. When you take a look at applying confidential computing to COVID scenarios, there's a few that come to mind. One is contact tracing, where you can combine different data sets. For example, Bluetooth low energy tracking plus GPS tracking plus information from travel systems like airplanes where users have been, so that you get a richer view of who might have been infected or just how the virus is spreading. One of the concerns with all the different data sources that are available from different healthcare providers, government organizations, corporations, is that their privacy concerns are limiting their willingness or an ability even to share those data sets with each other and get deeper insights out of them. And then finally, if we could combine these diverse data sets, we could also get better insights into treating the symptoms and understanding the behavior of the virus. Here's one concrete example that I want to show you on real data sets that can be combined to get deeper insights. Now, these are both public data sets. You can see a COVID-19 case database set from the University of Montreal, available on GitHub, and on the right side, a data set from the Radiological Society of North America. This one doesn't have anything to do with COVID. It's actually pneumonia-labeled chest x-rays. But by combining these two, we can increase the accuracy of COVID detections because they won't be confused with pneumonia detections. And in the case of these data sets coming from different hospitals or different organizations that might be unwilling to share their data or unable to share their data with each other, they can do so in a completely privacy-preserving way using confidential computing. So let's take a look at the architecture of the demo. You can see here in this slide, we've got the two hospitals, Hospital A and Hospital B. They each have their own subscriptions with their own data sets. Now, Hospital A is going to be where we run the confidential computing experiment. And so what we're leveraging is a DSV2 confidential VM. This is built using Intel SGX hardware, SGX being a type of hardware enclave that will protect the data while it's in use from even physical access to those servers. You can see that that is at the center of the picture, and that's where we're going to run our ML training algorithm. Azure Machine Learning is what we're going to use to create a learning pipeline that will take the data from those two hospitals and deploy it into that confidential VM where they get pre-processed and then trained, and then what will come out is a model. And that model then is encrypted and made available to both those hospitals. So now they can both take advantage of the deeper insights without having seen each other's data sets. Just because that VM is in Hospital A's subscription, it has no access to the data from Hospital B as it's being computed over in that confidential virtual machine. Now here I've got Visual Studio Code open, and you can see I've got several Python scripts here. The Python script 1 here is going to normalize that data set from the University of Montreal. And it's going to normalize it into a set of features. Remember, this is the COVID-19 data set. You can see here is the data set itself with the metadata in it with the different columns, including the patient information. Now, we've got a similar script for Hospital B, preprocess script 2. And then we have this merge Python script, which is going to take the results of those two preprocessed output files and merge them together into one data set. Now that data set's going to be computed over using a Docker container. That Docker container is going to be running a version of Linux, Alpine 3.1 that you can see there, that leverages a new capability that we've got, which is confidential Linux containers. With confidential Linux containers, you can place a Linux operating system and Linux compatible code into that enclave and process it. And what we're doing in this case is adding TensorFlow and a bunch of dependencies for the machine learning training into that container. Now when we launch the container, it's going to be ready to process that AML in that AML pipeline that we use a script to create. That script is going to do the pre-processing, do the merge, do the training, and then get the output model. The next step is to have each hospital encrypt and upload its data. This encryption process is going to ensure that nothing but that confidential container has access to the data. So that script ensures that it's talking to that confidential container, releases a key to it that allows that confidential container to decrypt its data set. Here you can see the hospital B also doing the same thing. And then here you can see, after we've done the deployment, the AML pipeline. Now, I've already run the training job, and so you can see the green ticks on the various parts of that training pipeline to show that they've completed. And once they've completed, we have our confidential model. That model, we don't necessarily even want to make available to anybody, but we can release it to the hospitals, also have it run in confidential enclaves, and then now they can submit queries to it, including chest x-rays, to ask the model, is it COVID-19 or not? And what you can see here is that we've deployed to the model and got back estimates on whether it's those models or those chest x-rays show pneumonia or COVID-19. So again, what we've just seen here are two hospitals fictitiously share these data sets that are different, coming from different sources, in a way where neither hospital got access to the other's data, and yet they were both able to take advantage of the better insights into prediction that resulted from combining them. So that brings me to the conclusion of the presentation. Azure was really architected to scale like this, from the people, the architecture, the processes that we've got in place, the 61 regions that we have, the trusted and compliant processes that we put in place to meet customer demand and understand the needs of our customers, with 200 services and the hardware and supply chain innovations that we've got, and the elbow grease we applied, for example, in the case where we pulled in DWDM hardware to expand our WAN from another region and borrowed it to expand capacity of our subsea cables, are all built on top of the expertise we've had in running Azure for the last decade. So with that, I want to thank you very much, and thank you for having confidence in Microsoft. And I wish you all health and safety during these challenging times.